ago in the second preceding problem, we kind of had the notion of what's referred to as a one-sided limit, and this will also help us to discuss continuity on a closed interval. The first thing we need to do is look at what we refer to as the one-sided limit. So the notation we've been using up to this point, when we say the limit as x approaches to c of f of x, when we say that this limit exists and is equal to L, what that really means is that whenever you approach c, and on a straight number line, there's two different directions in which you can approach c. You can approach c either coming in from the left-hand side, which we're going to denote as x approaches c with a negative superscript. Please be aware that that superscript does not mean negative number. It means a directional approach coming in from the left-hand side. Similarly, we can approach from the right-hand side. If I approach c coming in from the right-hand side, then we're going to use this notation. X approaches c with a positive superscript. Okay, that positive superscript does not mean a positive value. It means an approach coming in from the right-hand side. Okay. The limit itself, so the limit as x approaches to c of f of x will equal to L only when both the left-hand limit exists, the right-hand limit exists, and they both equal exactly the same value. Okay. One-sided limits can oftentimes be useful in taking the limits of functions involving radicals. For example, one of the things that we know as it pertains to radical functions with even integers for their index is that they're only defined for x greater than or equal to 0. So if I look at, let's just pick on the square root function here. This would be a even radical with index of 2. This function is defined for x greater than or equal to 0. And because of that, the only limit you can really kind of discuss at 0 would be a right-hand approach, because the function would be undefined for values of x that are less than 0. But certainly here we could ask the question, well, what is the limit as x approaches to 0 from the right-hand side of the square root of x? And we see that as x gets closer and closer to 0, coming in from this direction, that the function values are decreasing, and they would be approaching 0. Also, too, because we will say that the square root of x is right continuous at 0, we would be able to evaluate that limit via direct substitution. You can plug 0 in. The square root of 0 would be 0. In example 2, we want to find the limit of f of x equals the square root of 4 minus x squared as x approaches negative 2 from the right. So we want the limit as x approaches negative 2 from the right of the square root of 4 minus x squared. If you're thinking of the number line, here is negative 2, and we're approaching it, we're coming in from this direction. That's the positive direction. 4 minus x squared is continuous at negative 2, that polynomial on the inside. It's composed with the square root function, which is continuous at 0, so we can actually find this limit via direct substitution. Everywhere we see an x, we can replace it with negative 2, which is the value we're approaching. This is the square root of 4 minus 4, which would be the square root of 0, which would be equal to 0. It's fair to ask, and somebody might want to know this, well, why did we look at a right-hand limit as we approach negative 2 for this particular function, f of x? And the reason is that that's part of the domain of this function. If you looked at the graph of f of x equals the square root of 4 minus x squared, what we would actually see would be a semicircle centered at the origin of radius 2. So this function, f of x, isn't defined for values of x that are less than negative 2. So we won't be able to do a left-hand limit here, but we can certainly at least look at what's happening as x approaches negative 2 coming in from the right-hand side. And that right-hand approach, that limit's going to be the value of 0. One of the functions that's really kind of neat to investigate in terms of one-sided limits is what's referred to as the greatest integer function, sometimes also called the floor of x. The floor of x, so f of x equals the floor, is defined as the greatest integer that is less than or equal to x. So the greatest integer less than or equal to x. For example, if we want to practice computation on this, if I think of the number line, so here's 1, 2, 3, 0, -1, -2, etc. The number 1.5, so on the number line, 1.5 would be right here. Okay. If we look at the number of integers that are less than less than 1.5, there's infinitely many integers that are less than 1.5. 1, 0, -1, -2, etc. All of those are less than 1.5. But amongst all of them that are less, there's one that is largest, and that's the value 1. So 1 is the integer that's less than 1.5 and greater than all other integers. So we would say that the greatest integer of 1.5 would be equal to 1. Because it's defined as less than or equal to, if you have an integer, the greatest integer function of an integer will just be the integer itself. As another example, the greatest integer of -2.1, that would be -3. If you wanted to take a look and see what the graph of the greatest integer function would look like, it's an example of what we call a step function. And one of the things that we will see here with this kind of function is that it's going to be discontinuous at every integer. So every time you go from one integer, let's say 0, to the next integer, let's say 1, you're going to have a jump discontinuity there. Okay. In between integers is a horizontal line. It's a constant function, so it'll be continuous between integers, but you'll have a discontinuity, a non-removable jump discontinuity at every integer. In example 3, we're asked to find the limit as x approaches 0 from the left of the greatest integer function, and also the limit as x approaches 0 from the right of the greatest integer function. This is something that we could do with a table of values should we want to, but because we have the graph already available to us, let's go ahead and kind of investigate it. Let's first start by looking at the limit as x approaches 0 from the left of the greatest integer function. So on the number line, 0 is right here. If we're approaching 0 coming in from the left-hand side, what we see is that the function values are here, and we're consistently getting the output of -1. So the limit as x approaches 0 from the left of the greatest integer function is -1. Let's now take a look and see what would be the limit as x approaches 0 from the right of the greatest integer function. So now we're coming in and we're approaching 0 from this side. The function values are here. We consistently are getting the output of 0. So the limit as x approaches 0 from the right of the greatest integer function would be equal to 0. This is all the question asked for us, but I'm going to do one more thing. If we took a step back and if somebody asked us, well, what would be the limit as x approaches to 0 without any subscripts of the greatest integer function, the answer to that would be that that limit does not exist. When we don't when we don't put a subscript up top, they're saying or assuming that the limit from the left and the limit from the right would exist and would be equal to each other. But because we get a different left-hand limit than what we do right-hand limit at x equals to 0, this limit in general does not exist. This brings us to Theorem 2.10, which is the existence of a limit. Let's let f be a function, and let c and l be real numbers. The limit of f of x as x approaches to c is equal to l if and only if the left-hand limit as x approaches to c of f of x equals to l, and the limit as x approaches to c of f of x from the right is also equal to l. We can now use this notion to kind of extend our definition of continuity. Remember, continuity was first defined as a property of a function at a point. So continuity is defined pointwise. We were then able to define what it would mean for a function to be continuous on an open interval. So remember, open intervals means that the endpoints are not included. So any point in an open interval, let's call it the point C, you would have wiggle room from the left and from the right to approach. So you could look at the limits in general there. If we now want to extend the notion of continuity to a closed interval, a to b, then what's going to happen is the following. A function will be continuous on the closed interval a to b. So if I include this, if first of all, it has to be continuous on the interior. So for any point in between a and b, the function would need to be continuous. And then if we look at continuity at the left endpoint, let's call this the left endpoint a. To stay in that interval and approach a, you would have to do a right-hand approach. So we would need for the limit as x approaches to a of f of x to be equal to the value of the function at a. And if I wanted to look at a limit at b, again, staying within the interval that it's defined at, we would need to approach b but coming in from the left-hand side. So we would need the limit as x approaches to b from the left of f of x to be equal to f of b. So if it's continuous at the left endpoint, if it's continuous at the right endpoint in terms of the one-sided limits, and if it's continuous in the interior, then we would say that the function is continuous on the closed interval a to b. And intuitively, we're just kind of thinking of a graph like this. And you have a nice point where you start. Everything is nice and connected, no jumps, no breaks. We end up at b, which is also filled in. This is an example of a function continuous on a closed interval. Let's take a look and discuss the continuity of f of x equals the square root of 1 minus x squared. So this function, you can do a couple things here. First of all, the domain of this function is going to be the set -1 to 1 included. That would come from solving a polynomial inequality. So this function is defined wherever the thing underneath the radical, because it's an even root, would be greater than or equal to 0. This is a polynomial inequality. You would factor it. You could find the zeros of this left-hand side. Let's call that f. Maybe we shouldn't call it f because we already have a function. Let's call this, I don't know, maybe g. You could plot it on a number line. So we have -1, and 1 would be the zeros of g. And then if you do your sign test here, to test to see which regions, region 1, 2, and 3 would satisfy this inequality, it wouldn't be region 1, it wouldn't be region 2, but region 3, but region 2 would work. So the domain of this function would be all x's between -1 to 1, and that's also where this function would be continuous at. Its graph, if you wanted to do the continuity from the graph, this one would look like a semicircle centered at the origin of radius 1. Starting at x equals to 1, all the way until we get to x equals to +1, this function would be continuous. So f is continuous on the closed interval -1 to 1. There are many important properties of continuity that we will use. This is Theorem 2.11. Let's suppose that b is a real number and f and g are continuous functions at the point x equals to c. Then simply taking the function and multiplying it by a scalar, that resulting function will also be continuous at x equals to c. If you take two functions and you add or subtract them, then their results will also be continuous at c. The product of f and g will be continuous at x equals to c. And the quotient of f and g will be continuous at c, provided that the value of g of c is not equal to 0 to maintain and make sure that we're not actually dividing by 0. So pretty much what this tells us is as long as we take two continuous functions and we combine them with some of the most basic operations, just scalar multiplication, multiplying by a number, adding, subtracting them, multiplying them together, and taking their quotient with a non-zero denominator, then the results we get produce continuous functions. In example 5, it would follow that all of these functions listed below would be continuous at every point in their domain. So f of x here, the function x is continuous for all real numbers. E to the x is also continuous for all real numbers. Therefore, the sum of them, according to this theorem, will also be continuous for all real numbers. So f is continuous on negative infinity to infinity. If we take a look at g of x, wherever the tangent is defined, it will be continuous. Multiplying it by 3 will still keep it continuous. So g of x is going to be continuous wherever the tangent of x function would be continuous. Okay. If you're thinking of like unit circle, tangent we know is like what? Sine over cosine. So as long as the cosine isn't 0, which would happen at pi over 2 or 3 pi over 2, or really it's just any odd multiple of pi, you can continue to go around. So as long as x is not equal to some odd multiple of pi, we can write that as 2n plus 1 times pi over 2 for n any integer. Or I think for a lot of us, it might even just be as easy to say, k times pi over 2, where k is an odd integer. So as long as x isn't pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, etc., then this function g will be continuous. The last one we have is h of x. H of x is constructed by taking the polynomial x squared plus 1, I should say. That's continuous for all real numbers. The cosine of x is continuous for all real numbers. And according to the above theorem, this quotient function, h, will be continuous then anywhere except for where cosine of x would be equal to 0. And if we're just kind of keeping track, again, where the cosine of x would be equal to 0 in terms of a unit circle, it's the same places where the tangent would be equal to 0. It's that pi over 2 and 3 pi over 2 type of multiple. So h of x is also continuous for x not equal to an odd multiple of pi over 2. The next result we have is that of continuity of a composite function. Let's suppose that g is continuous at x equals to c, and that f would be continuous at the value g of c. Then it's the case that the composition function, f composed with g of x, will also be continuous at x equals to c. So if we take the composition of continuous functions, the result will be continuous. For example, f of x equals the natural log of x. Really not too much to think about in terms of a composition. It's just like a basic function here. But you might recall that the domain of the ln, you need the argument or the thing on the inside to be strictly greater than 0. So f is continuous on the set x greater than 0, which would be from 0 to infinity. In g of x, we have the composite function x squared plus 1, which is being composed with the square root function. X squared plus 1 is continuous everywhere, And then therefore the function g of x will be continuous, provided this part is defined where the square root is continuous. And that would be for wherever x squared plus 1 would be greater than or equal to 0. And that solution set's going to be all real numbers. X squared plus 1 is a value. Remember, x squared is always at least positive or at minimum 0. If you add 1 to it, you will always get a result that's going to be greater than or equal to 1. Therefore, g of x is continuous on all reals. And then the last one we're going to look at is h of x, which is equal to the tangent of 1 over x. 1 over x is continuous for all x not equal to 0. And then therefore the tangent of 1 over x will also be continuous, provided 1 over x doesn't give us a value where the tangent would be undefined. Well, where is the tangent undefined? Well, that would take place whenever the thing on the inside is equal to some odd integer times pi over 2. We can solve this for x. If you want to cross multiply, might be the easiest way to think of it. 2 equals k pi x. And then divide both sides by k pi. We get that x would be equal to 2 over k pi. So the function h is continuous. And I'm not going to write it in interval notation this time, but it's continuous as long as x is either not 0 or as long as x is not 2 over k pi for some odd integer k. Let's take a look at example 7. We're asked to describe the intervals on which the function is continuous. Here in example 7, our function f is constructed via the sum of e to the x and tangent of x. We know that the sum of these two will be continuous wherever the two pieces individually are continuous. Because wherever e to the x is continuous, and also where the tangent is continuous, then when we add them together, the result will be continuous. Well, e to the x, that is continuous for all real numbers. So e to the x doesn't have any issues. It's fine everywhere. We see that the tangent from earlier, that the x angle cannot be an odd multiple of pi over 2. So taken together, this function f will be well-defined and continuous, provided x cannot be equal to an odd integer of pi over 2.